All right, it says we're recording here. Got 22 people here to start our meeting, so that's pretty good. Okay, so let me open up my stuff here. I'm having trouble finding that for some reason today here. You guys are going to be excited because next week we're going to actually start on doing real stuff instead of all this vocabulary. I mean, it's good. It's a good basis for getting started, but I think it's not the most interesting, but it's good. So, all right, let me share my screen. Okay, so we're going to talk about 1.6, which is design of experiments. Okay, so last class we talked about observational studies. Today we're going to talk mostly about experiments. So an experiment is a controlled study conducted to determine the varying effects of one or more explanatory variables or factors. So generally what I'm going to call them explanatory variables, and then they will have a response, have on a response variable. So it's kind of funny. Statistics is funny because we have all these different branches and sometimes they call the same things different names, and so explanatory variables is probably what we're going to refer to more than factors, but in some branches of statistics they refer to them as factors. So any combination of values or factors is called a treatment. Okay. So this is another example. In an experiment, the experimental unit is a person, object, or well-defined item. Okay, so previously we've called that an individual. We're going to call that experimental unit in this section, but it's basically the same thing. So it's a well-defined item upon which the treatment is applied. We often refer to the experimental user as a subject when he or she is a person. The subject is analogous to the individual in the survey. Okay. So another term we need to know, we're going to talk about a control group, serves as a baseline treatment that can be used to compare other treatments. Okay. We're going to talk about blinding. Blinding refers to non-disclosure of treatment in an experimental unit. So there are two types of blinding, single blinding and double blinding. So single blinding, the subject does not know if they are receiving a drug or placebo. With double blind, both the doctor and the patient don't know. So sometimes a doctor may bias results by treating only those he thinks will benefit. And so a double blind study helps alleviate that problem. Okay? So I know I've gone over a bunch of new terms here, so you'll need to know those. But here's an example. Your homework I probably shouldn't give away the answers yet. So let's see if we can do this. Placebo-controlled double-blind study is done to see if Lipitor prevents cardiovascular disease. 2,838 subjects participated, aged 40 to 75 with type 2 diabetes, no prior history of cardiovascular disease. Subjects either took 10 milligrams of Lipitor daily, of which we had 1,479 subjects, or a placebo, we had 1,411. The response variable was a cardiac event. So, I know we talked about this last time, but hopefully you guys are good. We're going to start at the bottom of the list today because I think I started at the top last time. Zach Slater, are you on? Are you on camera?
Yes, I am. It took me a little while to get everything figured out, but the camera and mic both work good, I think.
Yeah, good. I can't hear you. Okay, so Zach,
okay.
Can you tell me what is the population in this study?
That would be the 2838 subjects.
No. Do we need to remember what population means? The 2838 is the sample, because there's more than 2,838 people in America, right?
Oh, would it just be all people with cardiovascular disease?
So that's a good start. So all actually without cardiovascular disease. Okay. So basically, here's your hint. Okay. This is your sample. This is your population. Okay.
Oh, okay.
So yeah. So give it to me again.
Okay, so the population is all people ages 40 to 75
People
with type 2
age
diabetes,
40 to 75 with type 2 diabetes
and then no history of cardiovascular disease.
and no history of abbreviate that CV disease. Okay. Yeah. So this is perfect. So yes, we're looking at all those people. So I guess they're only 40 years old to 75. Okay. All right. Good. So that's good practice. These will be the sorts of things. All right. So now, what was this? Well, I already gave away the sample, so I won't do that one. So the sample is the 2838 subjects with those characteristics. Okay. Now, I probably should have done this a little bit better, but notice that the placebo study and the drug study are different sizes. Now, part of that is due to the randomization procedure. Ideally, you'd want those to be the same, but a lot of times people will drop out if they don't think the drug is helping. So quite often the placebo group is almost always smaller than the drug group because people are like, this isn't helping, so why am I wasting my time in this study? And so this is just something that you're going to have to deal with. And so sometimes people will try to make the placebo study a little bigger because they know that dropouts are going to happen. But yeah, ideally we would like those to be, pretty close to the same. And these, when you're talking about 3,000 people, those are pretty close. So, all right. So, steps to designing an experiment. We need to identify the problem, and we need to be explicit. Don't say we want to see improvement because that is just vague. How do you know improvement is made? So let me give you guys an example here. When I was a student up at the University of Utah, I would work with physicians and professors that would want to create a study of some sort. And so this was a true scenario that happened upon me. So here's what happened. So a person was working on skin cancer. They wanted to do a study on skin cancer. And they said, okay, so we want to see, so basically, here's what she said. I'm going to teach a class, and I want to see if there's improvement in people's habits on trying not to get skin cancer. So my first question was, and this will be my question to you, how do you measure that? Okay, so that's a perfect example. Somebody wants to see improvement on people's habits with regards to skin cancer. How do you measure that? So let me throw that at you.
I think the first thing that I would measure is their use of sunscreen when they are spending significant amounts of time outside.
Okay, so that's good. So use of sunscreen. Now, my question once again is to be even more specific. How do you measure their use of sunscreen?
I think that you would make note of when they put it on before, how
So you're
often
going to
they
follow all
reapply.
3,000 patients around and ask them when they put their sunscreen on?
I think that would be a helpful way of doing it. I don't know if it's necessarily the best way. I
We're
mean,
going to have to recruit a bunch of students to follow people around and be stalkers, right? Okay, so this is what I mean. We need to be really explicit. How are you going to measure that? And that's good. I mean, that's one thing, but that's a lot of labor. That's very time intensive. Okay. What else? Or not only what else? What else is there that you could do to measure, or what would be an easier way to collect data?
I mean, maybe you could, with the sunscreen, you could give them a certain type of sunscreen you want them to use and like a certain amount, and just you almost have to assume that they use the full bottle or something.
Okay. Or, well, so here's a variation on that, Broderick. That's a good idea. You have to use this sunscreen. Come back in a week, and we're going to find out how much sunscreen was used. That might be a better way. Now, you're not following them around, and if they're in the sun for 8 hours, and it's only, 20-minute sunscreen. That might be a problem. But maybe you could measure it that way. That would be good. Okay. What else?
Maybe see if they purchased sunscreen more frequently than others. I don't know.
Okay, so I'm going to ask again, how do you measure that? Are you going to follow them around at the store? Because you got
No.
the same problem Whitney had. You guys are very surveillance oriented, I can tell.
So what's the original question again? We're trying to decide what.
Okay, so the doctor told me she wanted to see if there were improvements in people's habits with regards to skin cancer.
You could do a follow-up after 6 months where they fill out a survey to see if they use sunscreen, like how often, and you could have them fill it out before the class too, and the difference could help measure the improvement.
Okay, so Christian's come up with a much better, much less labor-intensive way of doing this, and that's to do a survey. Okay, you could have questions on there. Are you wearing a hat? Are you wearing a long sleeve shirt outside? And I like the pre-test, post-test. That would be a much easier way to collect data. Of course, Paul and Whitney, with the surveillance state, are going to probably be more accurate because people are probably going to tell you they wore a hat when they didn't, or they wore long sleeves when they didn't, and that sort of a thing. Okay, but I like Christian. He's going the right way. He's making this a lot less work on himself, so that's good, and also a lot less costly with hiring students to, be big brother and follow you around. Anything else?
So something that I know about skin cancer, whenever I have skin cancer in my family, and something that they ask you a lot of times is if there is a history of skin cancer in your family. So I'm not sure if that would mess up any of the data at all. You kind of have to look at the genetic side of it, I think, as well when you're picking these people to use for your experiment.
Well, so that would be some good background information. I don't know that. Well, I guess maybe you could figure out if people who have a history of skin cancer have better habits than people who don't. I mean, that might be something too. But yeah, once again, so a survey, I think that's probably going to be a much easier way. So I would just tell you really quickly, in this case, the person, kind of like what Christian said, had a pre-test and a post-test. Basically, she said she would walk into the classroom and she'd say, are you wearing a hat? Are you wearing sunscreen? Are you wearing long sleeve shirts? Blah, 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 before she lectured. And then she would lecture for an hour or whatever, however long it took. And then she would give them the exact same post-test with the exact same questions and see if they changed their answers. And hopefully they did. Although once again, yeah, so you might have had a test where you saw these gross pictures of people with, skin cancer removed and whatever, and you might have good intentions of wearing a hat and wearing a long sleeve shirt outside, and then, you just go about your daily business. So I don't know if that's a good way to measure improvement, but that's kind of what she came up with. So, all right, so once again, identify the problem and be explicit and think about how you're going to collect data, okay? All right, step number 2, determine the factors of variables that affect the response variable. Some variables that you should pretty much almost always include are age and sex, among other variables. Almost always with every study, there are going to be differences in age and differences in sex. So those, in addition to other variables, such as habits, are you wearing a long sleeve shirt, that kind of a thing. Those are always going to be want to be included. Determine the sample size. And on the book, they call this experimental units. For the rest of this, nobody's going to call it experimental units. We're going to call it sample size from here on. We're going to talk about sample size calculations later throughout the book. Okay, so and that will depend on your margin of error and money and things like that. So, all right, determine the level of each factor. So we're going to want to control and randomize. Going back to a skin cancer, maybe you could compare people that are using SPF 20 versus SPF 40 versus SPF 60, or probably a better experiment might be something to the effect of, in fact, let's do this instead. Let's say that you wanted to test fertilizer to see if plants were growing with and without fertilizer. So think about for a minute, and if you guys want to just shout these out or whatever, I'll pick on people too. If you're doing an experiment that where you're trying to grow plants, what are some factors that might affect plant growth besides fertilizer?
Sunlight exposure.
Sunlight exposure. Very good, Hayden.
Water.
What else? Say that again.
Water.
Water. Okay. I don't know who said that, but that's good. Amount of water, that would be good. So a little water, a lot of water. Okay. What else?
How many plants are surrounding the area?
How many plants are surrounding the area? You're getting into hard variables to measure, Whitney. But yeah,
if you keep the object in like a pot, or you set like a certain distance, and you can be like, you can keep the area clear of weeds or things. I think that would be, those things would make it easier to measure.
Let's see, does somebody have something here? Soil conditions, Jennifer said. You can speak up, Jennifer. You don't need to chat, but that's fine. So soil conditions, also a little bit of a harder thing to measure. Okay.
I think geographical location would be important.
Okay.
The weather.
Weather, that would be another good one. Thank you, Emily. Okay.
Insect activity.
Insect activity. Now, how can you control some of these things like weather and insect activity?
You could do a greenhouse.
A greenhouse. So that might be a good way. So with a greenhouse, we might be able to control sunlight. We would be able to control water because we're giving the water instead of waiting for rain and that sort of a thing. Okay. So so yeah, those are some great things. So we can control the amount of fertilizer, we can control the amount of sunlight so that they all get equal sunlight. We can control the soil so they all have the same soil. And of course, we're going to randomize the seeds to a certain plot of land. Okay. Step number 5 is to conduct the experiment. We're going to randomly assign subjects to the treatment groups, and then we're going to collect and process data. And then step number 6, we're going to test the claim. Okay. A lot of times we're either going to find confidence intervals or hypothesis tests. You'll know that when we get to confidence intervals and hypothesis tests, that's when this class is going to get hard. And the question is, can you infer these results are generalizable? Okay, now one of the problems is if we're putting it in a greenhouse, it's really nice because we can control sunlight, we can control water, we can control insects, we can control a lot of things. But it's also an artificial environment. Plants don't typically grow in a greenhouse, and so you may find that fertilizer X is really good for with 3 teaspoons or whatever and so much water, but when you get it out in the world, it doesn't work as well. And so that's one of the problems with experiments is quite often we put them in artificial environments, and so then when we put them in the real world, they might not perform the same way. And so they might not be as generalizable. Okay? All right, so now we're going to talk about different types of experimental design. So the first design we're going to talk about is a completely randomized design. Okay, and this means each experimental unit is randomly assigned to a treatment. So, all right, so here's the problem. A farmer wishes to determine the optimal level of fertilizer for a soybean crop. We want to design an experiment that will assist him. Okay. So here are the steps we're going to follow. So the farmer wants to identify the optimal level of fertilizer for growing soybeans. We identify optimal as the level that yields that maximizes the yield. Okay, so we're not talking about plant growth or anything. We want to have the most beans. So this is the response variable in this case is crop yield. So some factors that might affect crop yield are obviously fertilizer, precipitation, sunlight, the method for tilling the soil, the type of soil, the plant, and the temperature. Now the nice thing is if we do this in a greenhouse, we can often control the temperature. That doesn't always work when we're doing it outside though. But theoretically, all the plants will be treated the same outside. So in this experiment, we're going to plant 60 soybean plants. Also in this section, we're never going to call them experimental units from here on after this section. I don't know why it does that, but it does. We're going to call it sample size. Okay, so fertilizer is the factor that's going to be controlled. We're going to use 3 different levels of fertilizer, and we wish to measure the effect of varying the level of this variable on the response variable, which is yield. Okay, so we're going to set the treatments level of fertilizer as following. So treatment A, 20 plants are going to get no fertilizer. So this is kind of our placebo group. Okay. Treatment B, 20 plants are going to get 2 teaspoons of fertilizer per gallon of water every 2 weeks. Treatment C, 20 plants are going to get 4 teaspoons of fertilizer per gallon of water every 2 weeks. Okay. So this picture here that we've got, this is the kind of thing, it's hard for me to do this on a quiz, but on the I'm probably going to say I want you to identify or to diagram a completely randomized design. And when I ask that, I'm thinking of a picture like this. So the idea is we're going to randomly assign the plants to treatment. So we're going to have 20 plants in 3 different groups. Then we're going to give each group a different treatment, and then we're going to compare the yield. Okay, so when I'm asking you to do a completely randomized design, I'm asking you to draw a picture that's going to look something like this. Okay, so there are going to be various levels of factors in the completely randomized design. Precipitation, we can't control the rainfall, but we can control the amount of watering we do. So each plant receives the same amount of precipitation. Okay. Sunlight is also an uncontrollable factor, but hopefully it will be roughly the same for each plant. Hopefully we're not putting plants in shady areas and non-shady areas. Method of tilling, we can control this factor and use the Roundup method of tilling for each plant. Type of soil, we can control certain aspects of soil such as the acidity. Each of these plants are going to be planted in a 1-acre area, so it's reasonable to assume that the soil conditions are equivalent for each plant. There may be variation from plant to plant, so to account for this, that's why we randomize right off the bat. And hopefully, through randomization, all the plants will be similar. Finally, we've got temperature. Temperature is an uncontrollable factor, but it will be the same for each plant. Okay. All right, so step 5, we're going to assign each plant to a treatment group. We're going to number the plants 1 to 60, and then we're going to generate 20 random numbers. The plants corresponding to these numbers get treatment A. Then we'll number the remaining plants 1 to 40 and generate 20 more numbers. And these plants will get treatment B. And then the remaining plants will get treatment C. And now we're going to plant them and fertilize them according to our schedule. So at the end of the growing season, we're going to determine the crop yield. And then step 6, we're going to determine any difference in yield among the treatment design, the experimental design. And so anyway, that's the picture that hopefully you guys are going to get really good at drawing these pictures. Okay. So that's one type of experiment, and that is the completely randomized design. Okay. Now we're going to talk about another design, which is the matched pairs design. Okay. Now this is kind of like what we were talking about, was that Christian had mentioned doing a before and after test. Okay. The idea with a matched pairs design is the experimental units or the sample size are paired up. Okay. The pairs are selected so that they are related in some way. Okay. So one way to pair up is you're going to have the same person that's going to get a before and after treatment, or a pre-test and a post-test. That's exactly what we were talking about with the sun exposures and skin cancer. Another matched pairs design are twin studies. Those can be really interesting, twin studies, especially identical twins. Of course, you don't have to use the same person. We could pair up with a husband and wife. Maybe we'd compare the husbands versus the wives. That would be a natural pair. A geographical location. So there's lots of different ways. So with a matched pair, we're going to match them somehow, and there's going to be some sort of automatic pairing. So there are only 2 levels of treatment in a matched pairs design. Okay. One individual will receive one treatment and the other receives a different treatment. So unlike here where we had 3 different treatments, obviously with a matched pair, we're only going to have 2 different treatments. Okay. So the matched pair is randomly assigned to a treatment group using a coin flip or a random number generator. We're then going to look at the difference in the results of each matched pair. One common type of matched pairs design is to measure the response variable in an experimental unit before and after the treatment. So like a diet study, you could measure somebody's weight before they started the diet and then after. That would be another good idea for a matched pairs. In this case, the individual is matched against itself, or him or herself. Just one second, I need a drink.
Can I ask a quick question?
Yeah, go ahead.
So, like for the test, so with the matched pairs, for example, like do we need to know like step by step how it works? Just have a generalization of like how, like what it is.
So I'm going to give you a diagram, and I'd like you to be able to use the diagram. And so we'll give you a scenario, and more than likely, I'm mostly going to say, can you draw a diagram that represents a matched pairs design or a completely randomized design or whatever?
Okay.
All right, so experiments, there's sometimes, pre-test, post-test experiments. So here's an example of a matched pairs design. Educational psychologist wants to determine whether listening to music has an effect on a student's ability to learn. Okay, so we want to design an experiment to help the psychologist answer that question. So in this case, we're going to use a matched pairs design, and we're going to match students according to gender and IQ. Okay, and so we're going to probably put, now as I mentioned earlier, whenever we're doing an experiment, we should track gender and age. And so one of the problems is when we're doing a matched pairs design, if we put too many restrictions on there, we could maybe make them both smokers or both non-smokers, or both from high income or low income or whatever. And so sometimes that can, if we put too many restrictions on there, it can be hard to find a match. So in this case, what we're going to do is we're going to match based on IQ and gender, just those two. So we're going to match the students according to ID and gender. For example, we're going to have two females. Both of them have IQs in the 110s to 115 range. For each pair of students, we're going to flip a coin to determine which student is assigned to the treatment of the quiet room, and the other is assigned to the room with music playing in the background. Each student will be given a statistics test book and asked to study section 1.1. After 2 hours, the students will enter a testing center and take a short quiz on the material in the section. We will compute the difference in the scores for each of these matched pairs. Okay. Any differences in scores will be attributed to the treatment. And so this figure here illustrates the design. So remember, let me just back up here for a second. On the completely randomized design, we're going to randomize right off the bat. We're not going to do randomization on this. Okay, the first thing we're going to do is we're going to match students according to gender and IQ. So we'll find two 24-year-old females that have a similar IQ. Okay, and then step 2 is to randomly assign. Now, one of the things that I'm just going to point out here, very often on the quiz or on the test, people forget about this random assignment. And so they'll draw everything, but they won't randomize right off the bat. So remember, randomization is really important to the completely randomized design. And it's important here as well, but it's the second step rather than the first step, okay? So we'll randomize the treatment to each pair of students, and then we will administer the treatment and the exam to each matched pair. So we'll stick them in the room and then we'll have them take a test. And then for each matched pair, we're going to compute the differences in the scores on the exam. Now, another thing that I want to mention here, chapter 1 is really kind of the foundation for the rest of the class. And so one of the hardest parts about this class is I'm going to give you, and I don't think this is an exaggeration, about 15 different hypothesis tests and confidence intervals, okay? And so then I'm going to say which of these 15 hypothesis tests and confidence intervals should I pick for this test? And so part of that is based on, well, is it a completely randomized design? Is it a matched pairs design? And so understanding the type of experimental design will help you pick the proper test, okay? All right, so this is really, really important. One note about the relation between an experiment and simple random sampling. It is often the case that experimental units are selected to participate are not randomly selected. This is because we often need experimental units to have some common trait, such as high blood pressure. For this reason, participants are recruited to volunteer to be in the study. However, once we have these experimental units, we will then use simple random sampling to assign them to treatment groups. So with random assignment, we will assume that the participants are similar enough at the start of the experiment. Because the treatment is the only difference between the groups, we can say that the treatment caused the difference, okay? And so, yeah, if we're recruiting for people with high blood pressure or diabetes or whatever, obviously that's going to mess up our randomization, but we're still going to use randomization later, and hopefully that will be the cause of the difference, okay? Any questions on matched pairs design or completely randomized design before we move on? Okay. All right. Seems pretty good so far.
I do have one thing.
Okay.
It seems like the matched pair design would be more accurate than the other one, just because it's initially considering more variables and it's applying that into the experiment. Is that true?
It depends on what you're trying to do. Sometimes you're going to want to match pairs design. Sometimes you're not. Like with the seeds, the soybean seeds, there's not really a pair there. You're not going to be like, oh, I'm going to pair up these two seeds. You're just going to pick them randomly. So each experimental design has advantages and disadvantages, and it just depends on what you're trying to do. So
all right, thank you.
It's not that one is better than another. It depends on the situation whether they're better. Okay. All right, so randomized block design. Okay, this is our third experimental design. So this is used when experimental units are divided into homogeneous groups called blocks or strata. Within each blocks, units are randomly assigned a treatment. Okay, so a lot of times we call these a blocking variable. You can block on gender, age, or something else. Okay. So the idea here is, oh, I thought I had a diagram here. So a randomized block design. Now, let me give you, in fact, I'm going to try to draw a picture here. I thought I had one it's not in my notes, but randomized block design in a lot of ways looks a lot like the completely randomized design. But here's the issue, okay? So in advertising, maybe I'll add this into my notes here. So in advertising or drug studies, it is well known that women react differently than men, okay? And so just to tell you a true and sad story, back in the 1960s and 70s, I'm trying to remember what the name of that drug was, there was this new drug that treated insomnia. I'm trying to remember what the name of it is. But at any rate, they also found that it helped with nausea. Why can't I remember the name of this drug? Anyway, and so, a lot of times women, when they get pregnant, they have a lot of problems with morning sickness and nausea. And so they said, oh, well, this is a great idea. We're going to give these women, oh, why can I not remember the name of the drug? We're going to give them this drug. And
someone commented Bendectin.
No, it wasn't Bendectin. I can't remember what it was, but at any rate, they gave him this drug, and the terrible thing of it was it caused birth defects, and so they were giving it to pregnant women, and no, it's not Talmadom D. I don't know, I haven't heard of that one, but so they would give these women this drug. It would help with their morning sickness, and then their kids would be born with horrible, horrible birth defects. It was terrible. And so as a result of that, one of the things that they did was they said, okay, we're not going to include any women that are pregnant. And so they eliminated women from the drug studies. Now, so while that's great, we don't want to cause birth defects. We now don't know if any of our drugs are safe for women who are pregnant. And if they get sick, how do you know if it's safe and effective? And so it's kind of one of these catch-22 things. And so a lot of times, because of that, a lot of times, especially women have been excluded from studies because they didn't want to cause birth defects. But now we have all these drugs that have never been tested on women that are pregnant, and so we don't know if they're safe or not. And so it can be a terrible thing. So drug studies, it's well known that women react differently than men. Men are much easier because we don't get pregnant and we don't have to worry about that. So, but advertising is another case. Men and women often have different senses of humor. You know, men are going to laugh at more crude jokes, women are going to be more sentimental, and so that sort of a thing. And so basically, here's what I'm going to do. I'm going to draw a picture here. So a lot of times we will use what we call a blocking variable. So huge. And the blocking variable might be, shouldn't have done that, gender. Okay. And so rather than, so the easiest one to think about, and it doesn't have to be gender, but the easiest one to think about is we're going to break it into men and we're going to break it into women. Okay. And so we're going to block it into men and women. Okay. So once we do that, okay, we're going to take our men, and at this point we're going to randomize. We're going to randomize the men, we're going to randomize the women, and then we will split it into groups, okay? And I'm just going to do 2 groups because this is simple. I'm trying to keep it simple. You could have 3 groups or whatever. So you'll have group 1 and group 2, and you'll have group 1 and group 2. Okay. And then you'll assign some sort of a treatment. Treatment 1, treatment 2. I need to keep this smaller. Treatment 1, treatment 2. And then, excuse me, at the end, at this point, you will compare results. Okay. Okay. So you can see that basically this looks a lot like the completely randomized design, and I'll add this to my notes here. It basically looks a lot like the completely randomized design, but the idea here is we've used a blocking variable, in this case gender. So we're breaking them into men and women first, and it doesn't have to be men and women. I'm just using that as an example. And at that point, we will randomize and then add that to do that. Then treat the rest of it's just like the completely randomized design, but we're just breaking into groups first. So, any questions on that you guys have? Okay.
So are you saying like, so you have the men and you have the women, is you randomize the men and women into the group 1 and group 2, and is that the only time that randomizing happens, it looks like?
Yeah, so once again, I guess the point is, when do you randomize? So with the completely randomized design, you do it as step 1. With the matched pairs design, you do it as step 2. With a randomized block design, you're also going to do it as step 2 because you're going to break it up into men and women. Now, the other issue, I guess I should just mention here really quickly with the randomized block design, it is tempting to say, okay, you can compare the men to the men and you can compare the women to the women, but you should not compare the men to the women because this first step here is not randomized. You know, you're not randomly a man or a woman. I mean, I guess you are at conception, but yeah. So this because we've broken this up into men and women, we've already broken up the randomization right off the bat. So anyway, when you're doing a randomized block design, you can compare the men to the men and you can compare the women to the women, but don't compare the men to the women. That's an inappropriate comparison. So Does that make sense?
Yeah.
Okay. All right. So there you have it. I will post the notes. We're going to get done a minute or two early. Usually I go a minute or two long, so I'm going to give you back your minute. So Monday, your quiz on 1.6 is going to be due, and your homework will be due. Let me ask this question. And I'll do this with a thumbs up, I guess. Who does not have a book yet? And hopefully nobody puts a thumbs up on that. Oh, one person. 3 people. Okay. Maybe I'll put has a book. I am curious how many people have a book. Hopefully, usually most people have them by this weekend. So I should also see here. Oh, good. I'm glad. How many people do we have in our class? We're up to 25 here, or 24, I guess, if we don't count me.
For those of you who don't have a book yet, I actually found you can rent it on Amazon for $10 for the semester. Then you just send it back.
Really?
Yeah, it's pretty cool.
It's an electronic book, is that right?
No, it's an actual book. They send it to you, and then when you're ready to send it back, you just type in the little URL, and they'll pay for you to ship it back.
Oh, I've never heard of that before. That's a great deal.
Pretty neat.
Yeah. Wow, that's great.
That's what I did.
Okay. Okay, so we've got 17 of our 25 that have answered. That means hopefully the rest of you aren't just, goofing off and that sort of a thing. But all right. So yeah, great. Thanks, Hayden, for that. I didn't know it was so inexpensive. That's great. So all righty then. Well, see you all on Monday, and hopefully you'll do well on the quiz and homework. Also, we're going to actually start getting into some fun statistics instead of all this vocabulary. So that's going to be great. So, all righty then. I will let you go.
May I ask you a question?
Oh, go ahead.
You spoke a little bit about the a calculator the other day, but I don't remember what you said. Do you have a specific model or suggestion?
So my personal opinion is calculators are, especially graphing calculators, are highly overpriced. You can buy a Chromebook for the price of some of those TI calculators. So the main thing is, I don't think, if you don't have one, don't spend more than $30. You can probably get one for about $10 that will do everything you need. Just make sure if it will do standard deviation, that's the main thing. It should do everything that you need. For the most part, we're going to be using the tables in the book, and you're going to have to show me all your calculations. Yeah, 10 to 30 bucks is what I would spend. I know a lot of people use the TI 30, I think XS, the S stands for statistics. That's a good inexpensive calculator. Casio, I mean, everybody makes good ones. Casio, Sharp, I don't care really. But if you have a graphing calculator, I guess you can use it. We're not going to graph. You wasted a lot of money is all I'll say. But if you don't have one, just get a cheap calculator.
Okay.
Should be fine.
And did you put up the notes for 1.5 yesterday, or did I just not look in the right place?
Oh, did I forget? I might have forgotten. I'll make sure I get that up today.
Okay.
Anything else?
I think that's good. Thank you.
All right, you're welcome. Thanks.
Thank you.
Have a good weekend.
You too.
Thanks.
We'll see you. Go Jazz. If there's a game today, I don't know.